Hello, this is Andrew Stallard. This is my third video in the playlist for Electricity and Magnetism for Physics APC. We're going to continue our discussion of electric field, but not merely of point charges, but of continuous charge distributions. So without further ado, let's get started. We know the formula for the electric field of a point charge, Q, r squared in the r hat direction, where K is the Coulomb constant, whose value is 8.99 times 10 to the 9 in MKS units. Q is the charge, whose units are coulombs, and R is the distance between the charge and the point, and R hat indicates the field as a vector going in the direction of that distance. Supposing a charge Q, a point P, the field goes to point P from Q. Let's say now we have several charges. And we need to go and we need to find the field at point P. I'm going to call this point P right here. And so on. Now, if we have all these charges, we just take the sum. E is now going to be the sum. We have our sigma symbol. I goes from 1 to n charges. Q sub I, R sub I. Each charge is magnitude, and each one's distance. And we have to add these vectorially. Resolve them to components, add the components. Then find the magnitude resultant by Pythagorean theorem and the direction by arctangent. Add them as vectors. We know how to do that. Even if it's tedious, it's certainly doable. What if instead we don't have a point charge anymore? We have something like this. A string of continuous charge and we define this field at point P. And every part of this string is going to contribute to the field. Each one of these sections here is dl. Every part of the string. So the field is no longer a sum. It is an integral. Instead of summing up the charges, we're doing the integration. And a big mistake students make when setting up these problems, remember the integration is over dq. because we're summing up the charge, we're integrating over the charge. Don't try to turn this into dr. Now, for a line of charge like this, dq is lambda dl, where lambda is the charge density. Its units are coulombs per meter. Coulombs electric charge per unit length, the linear charge density. Suppose instead of a linear charge, we have a surface like this. In this case, say our point P is here. Every part of this surface, this charged surface, is going to contribute to the field. And now each of these are no longer dl, they are dA. The field is still integration of dq k dq over r squared. We take the k out of the integral, it's a constant, r hat. But now for an area, dq, sorry about my handwriting, is going to be sigma, small sigma, dA. Where sigma is the area charge density. The units for sigma are coulombs per square meter in MKS, charge per unit area. And again, if we have a surface, a nice surface, sorry, a three-dimensional volume, and we would define the field at point P. Every point here in this volume will contribute and the differential element of volume is now dV. The field equation rho dV K times rho dV over r squared in the r hat direction. And for a three-dimensional object, dq is rho dv and this rho, the Greek letter rho, is for your charge density. Actual charge, and this is an actual density. It's coulombs per cubic meter in MKS units, charge per unit volume. Just like mass density, you learn from mechanics, is mass per unit volume. Charge density is charge per unit volume. So, let's do some problems. Electric field due to a line of charge. We have a line of charge, line of positive charge goes from point A to point B. We think of the straight line as going straight along the x-axis. Because the charge goes along the x-axis. That's why we're integrating with respect to x. There's a dx here. Because of this, it's not a dy or a dr. R is the square root of x squared plus y squared. And this r hat, negative cosine of this angle theta, x hat plus sine theta y hat. This angle is supposed to be here. Sorry about that. Now cosine is adjacent over hypotenuse. Which is x over the radius, which is root x squared over r squared. Sine, opposite over hypotenuse. Y over the radius, square root of x squared plus y squared. This is negative because we're starting on this side where this angle is going to be, this angle is negative in the cosine. If we switch the order of integration, it would be positive. Our field, the x component of field, it becomes negative k lambda times x, because we have the r, and now this becomes r to the 3/2. We have r squared here, and we have this other r here. Here, r here, so it becomes not r to the 3/2, it's r squared, actually r squared to the 3/2. But it's x squared plus y squared to the 3/2. Because of the x squared plus y squared from the r squared, and the other r from the cosine and the sine respectively. And so we get this power. Now this integral is going to be tricky. This one is fairly simple. This is a u/du substitution. For the x, for the y, it's a trig substitution. A little bit trickier. We're not going to go over how to do the integrals here. There's any number of websites, videos, textbooks, you can learn how to do these integrals. But here's what we get. The x component and y components of the field. A charge string is 14 centimeters long, and the charge is 25.6 millicoulombs uniformly distributed. Now, uniformly distributed, that's all we're going to talk about at this level. That means the charge density is constant. What is the field? 10.3 centimeters from a point 4 centimeters from the end of the string. So, let's look at how we're going to do this. And again, we've got our, let's say, our string here. That's not good. I can't draw a straight line. There we go. Erase these. Let's draw another, see if I can draw a line perpendicular to that. Okay, I guess it just prints a straight line. This is awful. Okay, and it's also upside down, but here we go. This is the main charge string. This is, think of this as charged here. Oops. Okay. Okay. Positive charge throughout. This is just where the point is. We're going to be taking the integration with respect to this right here, since this is where the charge is, okay? Respect to x. Now, where are the limits of integrations? This is 4 centimeters. So we're going to start here. This is 10 centimeters in the other direction. So for convenience, we're going to call this the origin. This is going to be 4 centimeters. And this is negative 10 centimeters here. And this here, 10.3 centimeters. Like I said, the drawing is not to scale. Now, when we do this, it's going to be the integration of k lambda dx r cubed cosine theta r squared. It does become r cubed because this becomes cosine theta is x over r. So let's do this. We have k lambda x dx all over r, which is still, r is still the square root of x squared. This is always r. R is still Pythagorean identity, root x squared plus y squared. X squared plus y squared. To the 3/2. And so let's put in the numbers. The upper bound, to keep the units consistent, is 0.04, and the lower bound is negative 0.1. Keep the units consistent. We got to keep them in meters. That's in centimeters, convert to meters. K is 8.99 times 10 to the 9 Now the charge density is the charge per unit length. It was 25.6 millicoulombs, so that's 25.6 times 10 to the negative 3. Convert millicoulombs to coulombs. .6, and this is the length, which is going to be 0.14 meters. And y and x is a variable, okay? And we give x squared plus y squared to the 3/2. The 0.103. Y is always this. Y is a constant. And after we take this integral, we get our k. Our lambda (25 times 10 to the negative 3), 0.6 times 10 to the negative 3, over, which is going to be, of course, lambda. It's the charge over the length. And it's going to be 1 over the square root 0.04 squared plus 0.103 squared, okay? Now, going back to the formula here, the x is the only thing that's changing. X hat's always the same. Lambda, k, and y is constant. So this k lambda is always going to be the same. So when we do this problem, we put this in. It's a Pythagorean identity, square root of x squared plus minus y squared minus 1 over .04 squared plus 1.103 squared square root, okay? And when we do that, the x component of the field is going to be 3.47427 times 10 to the 9 newtons per coulomb. That's going to in the x hat direction. Now, to find for the y hat direction. It's going to be k lambda x over y all over root x squared plus y squared evaluate the upper bounds. I'm not going to bother going through the integral again. This is just the answer to the integral. And we have our bounds 0.04 and -10, -0.1. And again, we plug in the numbers. 8.99 times 10 to the 9. Y is 0.03, 0.103 meters, 10.3 centimeters. K is the charge, 25.6 milliliters divided by the length, which is 14 centimeters. Now this part here, we're going to plug in 0.04 in for x, and then we're going to plug in -0.1 in for x, okay? And subtract them. And of course, we'll have negative, negative, that will be a positive. And what we get is 8.322 times 10 to the 10 newtons per coulomb. Now, to find the magnitude, we use the Pythagorean theorem. Square root of this squared plus this squared. These are the x and y components of the field, and so we get 8.39 times 10 to the 10 newtons per coulomb. And then we take the arctangent of this y component over this x component, and we get an angle of 87 degrees. So I'm going to redraw this. So I can draw a straight line. This field at this point here, this is the E field, it's almost straight up, okay? It's going to be an 87 degree angle. Why do you think that is? Why do you think it's mostly in the Y? Because look what's happening here. Let's look at these field lines here. In the X, the fields on these two sides are fighting each other. But in the Y component, they're all working together. They're working against each other horizontally, working with each other vertically. So, what's the general formula for an electric field for a line of charge for a point halfway between the ends? If it's halfway between, there's going to be no field whatsoever in the horizontal x direction. It is all going to be in the vertical direction. So if you look at something like this, These are exactly halfway in between. Don't know if they are, I'm not good at drawing. If these are, let's say, halfway in between like this, they're going to the fields from these charges, this charged rod, are going to cancel each other out in this direction. They're going to reinforce in the y. So the whole thing is going to be in the y component. E is going to be K lambda x y square root of x squared plus y squared in the y hat direction from, we'll call this point A, call this point negative A, from A to negative A, and we put these bounds in. We're going to put A in for x here, A in for x here. When we put negative A, when we subtract them, negative is going to be a positive. We put negative A in squared, and we still get A squared. So this whole thing is going to be 2k lambda A y square root of A squared plus y squared. Now, what happens when A goes to infinity? What happens if we keep making A bigger and bigger? Notice we take the limit as A goes to infinity. That means we're extending this out in both directions. These are going to go away. We have a linear power of A in the numerator and the denominator. The y squared isn't going to matter here, okay? So what we have is $2K lambda over y. Or 2k lambda A over y. Lambda. So again, that's units of electric field. Lambda is coulombs per meter. So those units make sense, and this is what happens as we go to infinity. Electric field to a ring of charge along an axis of symmetry. In the example on the right, the point P is along the axis of symmetry, so there's no field along the radial direction. Now, we could do alternative point P here and get a general formula for the field. That would be really complicated. We could do it, but let's do something simpler here. Find the field along the z direction of a ring of charge. Here, dq, this is the tricky part, dq is r d theta. For an arc of charge times lambda. Of course, linear charge density. An arc of charge, it's r times d theta. The only thing is changing. The variable here that's changing is theta. So we find the field. Notice is going to be E is still integration lambda r k lambda r d theta over r squared. But what's r here? R is this. Is the square root of r squared plus z squared. Okay? Now, for the vector hat z hat, that's going to be the cosine of this angle phi. And the cosine of phi is z over the radius, over the r, the distance, not the radius. This now becomes 3/2, and this becomes just z here. So you have the integration of k lambda r d theta. We're going on the full circle, so it's 2 pi to 0. But notice, this is a simple integral. We're doing the integration with respect to theta, but all that is there is d theta. So this is just 2 pi k lambda r all over rz all over r squared plus z squared 3/2 in the z hat direction. Again, it's an easy integral once you set it up. What is the field 10 centimeters above a ring of charge of 4.5 microcoulombs in a radius of 6.0 centimeters? So let's do this formula. It's going to be K times 10 to the 9 so let's just write it out again. E is going to be K lambda R Z two pi R squared plus Z squared to the 3/2. This is your Z hat direction. K is still 8.99 times 2 pi is still 2 pi. K is still 8.99 times 10 to the 9. I'll do it on this. Here. Two pi times 8.99 times 10 to the 9. Here's your 2 pi, here's your K. Now what's lambda? Lambda is going to be the charge, which is going to be 4.5 times 10 to the negative 6, because it's micro, okay? Change the microcoulombs to coulombs, over the length, which is going to be 2 pi r, which is 2 pi times 6 centimeters. That's 0.06 meters. Okay, now these 2 pi's cancel out here and here. We got to multiply this by r, which is again is still 0.06 meters. And now these cancel out here. By multiply this by z, which is 10.0 says is 0.1 meters, which is 10 centimeters. And we have to divide it all. 0.06 squared plus 0.1 squared, all raised to the 3/2. Now you put that in your computer or calculator. What you get is 2.55 times 10 to the 7 newtons per coulomb, all in the z hat direction. Now let's look at the next problem. What happens when z is much larger than r? Two pi k lambda z three halves. And there's another r here. Sorry. Now, when z is much bigger than r, this is going to be irrelevant since we're adding r. This becomes z squared to the 3 halves, which is z cubed. These z's now cancel out. We have z squared in the denominator. Now 2 pi r lambda. Lambda is the charge density. 2 pi r is the length of the charge ring. So, what is that? The linear charge density times the length is just the charge. So 2 pi r lambda is q. We have kq. So we are left with kq all over z squared, and this was in the z hat direction. Now you should recognize this formula. This is the Coulomb's law for the field of a point charge. As we get further and further away from the ring starts to behave the same as a point charge. That's going to be an important idea coming up. So how about this? A semicircular arc of charge q surrounds a point C at a distance r. What's the field at C? Okay, so we need to find this field. So we have, the field is going to be integration dq over r squared in the r hat direction. Let's look at this. The first thing we can do is make a symmetry argument. This entire field is going to go this way. Okay? Because look at this. Look at the components of here. The components in the top, the y component, the horizontal component, is going to completely cancel out the component on the bottom. So let's keep going. dq is going to be lambda r d theta. R is just going to be the constant r. So let's look what we have here. We have lambda r d theta all over r squared times k. This is going to go from pi over 2 to negative pi over 2. Now we still need to multiply this. We still haven't taken into account the r hat. R hat is cosine theta x hat plus sine theta negative cosine of sine theta y hat. And as we said, this goes away. R is just cosine theta x hat. What's the cosine of theta? Cosine is adjacent over hypotenuse. Or no, wait, no, make it easy. We can just do this in terms of theta. Okay, no, this is going to be positive. Okay, so we take the integration of cosine of theta, because this goes away here. So you have the integration of cosine, and we get sine. From pi over 2 to negative pi over 2. And we have 1 minus 1, which is 2. So when it's all said and done, we get 2k lambda all over r. Now, this video is getting very long now, so I'm going to stop this right now, and next time we will cover surface and volume charge distributions. Thank you.